Internet Protocol version 4 or IPv4 design. In this video, I'm going to talk about IPv4 design. Actually, at the first step of IPv4 learning and also learning about the design of IPv4, we are talking about the IPv4 header. This is the first step. Actually, one of the most important features related to IP or Internet Protocol is the header of IP. Because of that, at the first step, we should know about different fields and multiple fields that we have in the IPv4 header. Because of that, first we are starting our knowledge or learning about the IPv4 design with the IPv4 header. You know that according to the TCP/IP model, okay, IP or Internet Protocol is a protocol that is working in the layer 3 of the TCP/IP model. And also, you know that IP is the abbreviation of IP or Internet Protocol. And also, we know that the transport protocols means TCP and UDP. Okay, TCP is the abbreviation of Transmission Control Protocol, and UDP is the abbreviation of User Datagram Protocol. Okay, should create a segment. And after that, the segment should be sent to the IP or Internet Protocol. As you can see here, TCP and UDP should send their segments to the IP. And after that, IP should create the IP data or packet or datagram. We call it packet. Actually, when we are giving the, for example, segment to the IP should give us packet or datagram. You know that IP is described in RFC 791, and IP was prepared for the Defense Advanced Research Project Agency or DARPA in September 1981. Now let me to explain the IPv4 header. Here we have one simple scenario. I have configured this simple scenario. We have two router 1 and router 2. I'm going to use this simple scenario only for verification of the IP header. You know that this is the IPv4 header. I will explain all of the fields in this video, and also all of the fields in this, for example, header. Let me first emphasize that the IPv4 header is 20 bytes actually in length. Actually, IPv4 header without IP option, okay, has 20 bytes. And when we are adding IP options for some specific reasons, maybe the IPv4 header size is increasing. Because of that, until now, we have learned that the segment should be sent to the IP, and after that IP create the packet or datagram. And we know that one of the most important features that we have in the IP is the IP header, and now we are talking about the IP header. IP header without IP options and also padding has 20 bytes length. Look at here. Here we have 20 bytes length, and it means that we can say the IP header in most cases has 20 bytes in length, but in some rarely cases that we have IP option field and also padding, maybe the header of IP is increasing about the size. Okay, now I'm going to show you first one simple IP header, and after that we will learn about the content of the IP header. It is so easy and also so interesting. Look at here. For example, we can capture the link between the router 1 and router 2. It is so easy. And then we can send a traffic from router 1 to router 2, or if you want, you can use telnet protocol to send telnet session from R1 to R2. Let me to use, for example, ICMP or ICMP echo request, router 1, ping 10.122. Now we have connectivity. Okay, and this is the result of our capture. Let me to stop it here. You can see we have ICMP echo request and then ICMP echo reply. Here we can see the packet. This is for example, Internet Control Message Protocol or ICMP. ICMP is a protocol that we have in the layer 3, and it should send its traffic, it should give its traffic to the IP. Here you can see that we have ICMP, then IP, then Ethernet, and this is the layer 1. As actually Actually, here we can see the content of this, for example, data. Then here on the Internet Protocol version 4, we have some information. Here you can see these informations here. Let me to compare the header of IP that we have captured with this figure. Look at here. We have the first field, the version, I will explain it, and then the internet header length, IHL, and after that here we have type of service. This is the type of service. Actually, here we have two fields, differentiated service code point and ECN. Both of them, okay, are calling the type of service or TOS. This is the new name of TOS. I will explain it. After that we have total length, and then we have identification, and then we have flags, and then fragment offset, then time to leave, after that protocol, and after that for example header checksum. Then here we have source IP, destination IP, and this is the real data. You know that here we don't have IP option field and padding. Only in some rarely cases we can see the IP options and also padding. I will explain them. For now, let me to start talking about the different fields that we have in the IP header. The first field is the version. As you can see, version has 4 bits length. Look at here. Here we have 4 bits length. Okay, and here we can experience one of these two value. The first value is the 40, okay, as 110. 0110 is equal to the 4, and also it is possible that we see for example here 0100 means 4, and also it is possible to see 0110, it is equal to 6. What does it mean? With version, actually we can understand this is the IPv4 header or IPv6 header. I will explain the IPv6 header in future videos. Now we are talking about the IPv4. Because of that, we expect to see always in these 4 bits, in these first 4 bits, the value of 0100. Actually, with these 4 bits, the receiver can understand this is the header of IPv4 or this is the header of IPv6. Let me to show you the, for example, version. Here in the capture file, this is our capture, we can see that in version we have 0100. It is so easy. This is the first step, and we know that it indicates the IP headers format based on the version number, and we expect to see 0100 for IPv4 and 0110 for IPv6. This is the first field that now we know about it. Look at here, this is the version. Alright, now let me to explain the next field. The next field is IHL or Internet Header Lengths. As you can see here, again we have 4 bits, okay? And this field IHL indicate the length of the header in 32-bit word. You know that if in IP header we don't have IP options, the length of the IP header is 20 byte, okay? I have explained it before. Because of that, here maybe you expect to see the value of 20, but actually here we can see the length of the header in 32-bit word. 32-bit means 4 byte. Actually, because here now the length of this header is 20 byte, we expect to see the value of 5. Okay, 5 means 0, 1, 0, okay, 1. It means that here now we have the value of 5, and 5 means 20 byte, okay? And because at least we expect to see 20 bytes, the minimum value in the IHL, okay, is the 5. And if we have option fields and also padding, we will experience the values more than 5. Here, let me write here, this is the version 0100, and then in IHL we expect to see now 0101 means 5, but 5 multiplied 4 byte equal to the 20 byte, and this is the length of the header. Don't forget, this is only the length of header, not the data. Actually, when we are, for example, sending ICMP, let me to show you, this is our ICMP, okay, and after that we have ICMP echo request, and after that we have 20 bytes IP header. We are sending this packet to the router 2. Router 2, after for example verification of this field, the IHL field, can understand after which number of bytes, okay, it can reach to the data data, to the real data, to the ICMP. For example, it knows about the start of the IP, and it knows about after, for example, 5 multiply 4 means 20 byte, okay, it can reach to the real data. It is so useful. Let me to show you the value of IHL. Here you can see that the value of IHL is 5, and this is the header length, and as you can see the value is 5 equal to the 20 bytes. It is so easy. The next header is the type of a service or TOS. Here, let me to write it here. We have a field, we call it TOS or type of service. Okay, we are using TOS or type of service for giving priority to the packet. Actually, we are using type of service in quality of service courses. Okay, quality of service or QoS. For understanding the TOS, okay, I will give you more information about this field. Because of that, for now, let me to say only that type of service or TOS has 8 bits in length. Okay, and when we want to implement quality of service for some type of traffics, we can use this field, and because of that, I will explain it a little more in this video. For now, let me to say that here we have 8 bits, and the 8 bits can be between 80, okay, to 81. It is so easy. I will explain it, don't worry. And this is related to quality of service 80, or maximum value is 81. I will explain it, don't worry. After that, we have total length. About the total length, as you can see here, we have 16 bits. Okay, what does it mean? Here we have one header IHL, and this is the internet header lengths, and also here we have total lengths. Here we have 2 type of lengths. Okay, the first length IHL is indicating the length of the IP header, only IP header. Okay, but with total lengths we can understand the length of the total packet. Okay, means include the data. Actually, it represents the length of the datagram or packet in byte, including the header and data. And in most cases, we are using the, for example, total length for understanding that this packet should fragment it or not. Look at here. Each interface, as you know, has one value. We call it MTU. MTU is the abbreviation of the maximum transmission unit. Let me write here, maximum transmission unit. And this is the maximum size of packet that can be sent from this interface. If we have a packet larger, okay, than this size, we should fragment it, and after that we can send it. Okay, because of that, we are comparing the total length with the MTU. For example, MTU by default is 1500 byte. If the total length is bigger than the 1500 byte, we should fragment this packet. Actually, we can say the minimum value that we have in the total length is 0. Okay, you can write 16 zeros, and the maximum value is equal to the 2 to the power of 16, okay, minus 1. Okay, this is equal to 65,535. Okay, actually here we have a value between these two values, and the maximum length of an IP packet, okay, is using to determining whether fragmentation is necessary by comparing the total lengths with the outgoing interface MTU. Here, let me to show you the total lengths. Here we have total lengths of 100 byte, and as you know, 100 byte is smaller than the MTU of interface. Because of that, we don't need to fragment the interface. Here in the R1, if you want, you can use show interface fast Ethernet 00. You can see that the MTU of interface is 1500 byte. Because of that, we don't need to fragment the traffic. That's it. Okay, now let me to talk about the next field. Until now we have learned about the version, IHL, type of service. I will explain type of service with more detail, and after that total lengths. Now let me to talk about identification, flags, and also fragment offset. Let me to say that in most cases, we are using these three fields, identification, flags, and fragment offset, when we are experiencing the fragmentation. Okay, for example, because the total length of the packet is bigger than the MTU, we are using these three fields, fragmentation. But before talking about the fragmentation, let me to say that we can use identification for other reason. The first thing that you should know is that, as you can see here, identification has 16 bits in lengths, and after that here we can use it in fragmentation, and also we can use it in normal traffic forwarding. How? Look at here. This is our capture. In the first ICMP, this is the first ICMP echo request, and this is the reply of this request. Again, ICMP echo request, then reply for this request, then request, then reply. Okay, as you can see here, as you can see in the first request, ICMP echo request, we have identification set to this value 10. Actually, here we have 16 bits, and the value is in the decimal is equal 10. As you can see, the reply is receiving with the same identification, and we can understand this is the reply of this request. Okay, it is so interesting. In the next request, as you can see, we are using other value, for example 11, and the reply is also 11. It has identification of 11. What does it mean? It means that this is the reply of the, for example, 11 request. And then in the next request, we are using identification 12, and this is the reply of the, for example, we have a reply of 12 and then 13. Okay, and here you can see 13. Because of that, we can use identification for understanding which reply is received for which request. Okay, but in most cases, we are using identification to understand, to discover that this fragment, okay, because it is a unique identifier that denotes fragments for reassembly into an original IP packet. Let me to explain it. Look at here. Assume that we have a packet with the, for example, 1000 bytes lengths. Okay, here we have 1000 bytes or 2000 bytes, okay, lengths, and because the MTU of this interface is 1500 bytes, we should fragment it. Okay, we are fragmenting this packet in two packets. Okay, the first packet has 1000 bytes, okay, and the second packet has for example 500 bytes. Let me to show you. And we should send it to the router 2. You know that after fragmentation, we expect to, in the router 2, for example, we experience the reassembly of these two fragments into one packet. This is our two packet, but you know that it is possible that we receive at the same time other packets. For example, we are receiving the next packet. Let me to show you with another color. And here, for example, we have the next 2000 byte, and again, we should fragment them. And as you know, the router 2 should know which fragment is received for which, for example, non-fragmented data. How it can understand? Here we don't have any, for example, tools. Because of that, we should use identification. Actually, here you are using, for example, identification of 1. This is one assumption, and here we are using identification 1, and again here we have identification 2, and then identification 2. What does it mean? It means that the router 2 now can understand which fragment is, for example, corresponding to which real data. And here at the router 2, we can reassemble these two packets to these two fragments to one, for example, packet. Also, we have fragment offset. With fragment offset, this field, as you can see, has 13-bit length. Let me write here. The identification has 16 bits length, and here we have 3 bits for flags. I will explain the flags. And also here we have 13 bits for the fragment offset. This field is 13 bits in length, and it indicates where in the packet this fragment belongs. Okay, it is so easy. For example, here we are sending the first packet with the fragment offset. This is the fragment offset 0, and this is the fragment offset 1. Okay, and maybe in the next packet again, this is here we have the fragment offset 0, and here we have fragment offset 1. The values is not important. But in the router 2 now we have two tools. With identification we can understand which which fragment is belong to which for example real data, and after that in that real data we can understand the order of the fragments. For example, here the first fragment, this is the second fragment, we can reassemble them into one packet. It is so interesting. Okay, because of that, with the help of identification and fragment offset, we can reassemble the fragmented packets into for example one packet. It is so interesting. Let me to show you one example here. Again, we should capture this link, and this is the new capture that we have. Okay, now in this new capture I want to show you the fragmentation process. For example, in R1 we can send packets with the size bigger than the MTU. For example, here I'm going to use ping command again, 10122, but with the size of 2000 bytes. Okay, here we can see the size of 2000. We have connectivity, but here now we have fragmentation. Let me to stop this capture. Look at here, 10121 to 10122. As you can see here, we have fragmented IP protocol. Let me to explain these two packets. Both of them are belonging to one packet. Look at here. This is the first 10121 to 10122. In the IP header, you can see that we have identification of the 17, and in the second also the identification is 17, as you can see. Because of that, we can understand both of them are residing in one real packet. And after that, in the first packet 10121 to 10122, we have the for example total length of 520 bytes. Actually 500 bytes is for data and 20 bytes for the header. And in the next packet you can see we have 1500 only data, because the header only is available in the first packet. Okay, actually let me to show you. It is interesting to understand that here we have data. This is ICMP data, and the size of data is 2000 bytes, because I have used the ping to the 10122 with the size of 2000 bytes. Okay, and also we have IP header. IP header has 20 bytes. Okay, when you want to send this traffic and the MTU is 1500 bytes, we need to do the fragmentation. Okay, because of that, now we have two packets. The first packet is going with the size of 500 bytes of data and also 20 bytes of the IP header, and total length is equal to the 520 byte. And after that, here we will have the next packet. The next packet has 1500 byte of only data. Here we don't have any header, because here the identification of both packet is 17. At the router 2, the router 2 can understand these two packets are belong to one for example non-fragmented data. Also, let me to show you the fragmentation offset. This is the fragmentation offset. Here in the first packet we can see that fragmentation offset is 1480, and after that here we have in the next packet, let me to show you, this is the for example first packet. The first fragment offset is 0, and then as you can see 10121 is for example 1480. Okay, and after that here this is the ICMP echo request. Let me to show you fragmented IP protocol and ICMP echo request, and for example so on. This is the 10121. Let me to show you again. This is 10121 with the for example identification of 15, and here also we have 15. We should compare these two. Look at here, 10121 fragmentation offset 1480, and then here we have fragmentation offset 0. Then because of that, in the router 2, when it is receiving two packet, okay, or two fragment with the same identification, it can use the fragment offset to gather the information. Okay, also we have 3 bits, and these 3 bits are the flags that we have in the IP header, and these 3 bits are related to the fragmentation. Let me to show you. It is interesting also. Here in the flags, this is the flags that we have 3 bits. The first bit, or the here we have bit 0, bit 1, and bit 2. Okay, this is bit 0. Bit 0 is reserved bit and we don't use it. Actually, here we have this field is 3 bits in length. It indicates whether the packet can be fragmented and whether more fragments follow. Bit 0 is reserved and is set to 0, as you can see. Bit 1, here we have DF bit. Actually, this is the DF bit, or don't fragment bit. In some cases, we don't want to fragment this packet. We can set this for example, flag, and it means that you shouldn't fragment it. In some cases, for example, when we want to discover MTU of the path, we are using this field. And here, as you can see, with more fragment, we can understand we have more fragment about this packet. For example, here, look at here, the identification 15, more fragment 0, and here we have identification 15. Okay, means more, and here you can see that more fragment is available. Actually, it means that we have more fragment for identification 15, as you can see here. The first is 0, the second is 1. Okay, actually here we have 3 bits, bit 0, bit 1, and bit 2. Bit 0 is always 0. Bit 1, when we don't want to fragment the packet, is 1, and in the normal cases it is the packet can be fragmented. Because of that, it is set to 0, and more fragment means that here we have fragmentation. Let me to show you one example about the DF bit. Here I'm going to explain it a little more. Look at here about the flags. I'm going to write them here. About the flags, the first bit is reserved. Bit 0 is reserved and always is 0. And after that, the bit 1, this is the bit 1, we call it the DF bit, or don't fragment bit. This is by default is 0, and you can change it to 1. It means that you shouldn't fragment it. For example, in the router 1, look at here, we can use the ping, okay, and then 10.122. Here we have some options. Okay, one of them is DF bit. Enable do not fragment bit in the IP header. I want to show you what is happening. Here I am going to enable again the Wireshark capture. Okay, after that I want to show you what is happening when we are sending a packet from the R1 to the router 2. This is R1 with the DF bit. Ping 10.122 DF bit. Okay, here as you can see we have connectivity, and here you can see that in the IP header DF bit is set. Okay, but here we don't have any problem because the size of ping is 100 byte and the MTU is 1500 byte. Because of that, here we don't have any problem. Assume that we are using ping 10.122 with the size of the for example 2000, and also with DF bit. As you can see, we cannot send traffic, and here the fragmentation doesn't work. Why? Because with DF bit you shouldn't consider, you say that I don't want to fragment this packet, and because the MTU is 1500 byte and the size of packet is 2000 byte, you cannot send the traffic to the router 2. Look at here. Here it is obvious that we don't send any traffic to the other site. Okay, this is the functionality of DF bit, but about the usage of DF bit, you will learn in more in other videos that we are using DF bit for pass MTU discovery. For example, we can increase the size of packet, and in each time that the for example connectivity is not available, we can understand this is the maximum MTU that we have in the pass, or maximum available MTU. Actually, this is the minimum MTU of all MTUs that we have in the pass. Also, you know that about the bit 2, I have explained that the bit 2 is the MF bit, or more fragment bit, and only when we have fragmentation we will see the for example more fragment bit set to 1. Okay, because of that we can understand these 3 fields: identification, flags, and fragment offset. All of them are related to the fragmentation feature, and if we don't have fragmentation, only maybe identification field is using. All right, now Let me to talk about the time to live. You have learned about the time to live in the CCNA class, and we are using the time to live or TTL with the 8 bits length for preventing remaining one packet for infinity in one routing loop. Okay, here I'm not going to talk about the detail, but you know that when we are sending a packet from router 1 to the router 2, in the IP header we have the TTL value, for example TTL 64. Okay, when the router 2 is receiving this traffic and the router 2 wants to forward the traffic to the next router, it should decrease one value from the TTL, and if the TTL is reached to 0, the packet should be dropped. For example, assume that we are sending with a packet with TTL of 64 to router 2. Because of some problems, some routing problems, the router 2 is forwarding or sent back this packet to the router 1 after decreasing the TTL. Again, the router 1 should forward it to the router 2. The TTL is 62. Again to the, for example, router 1, the TTL is 60, for example, 1, and finally it can reach to the TTL 0, and we should drop the packet. I will explain it a little more for example, in this video. Alright, this is the TTL functionality, and after that we have the field protocol. You know that the field protocol can show us which application is sending this packet, or which layer 4 protocol, okay, or application in some cases is sending this traffic. Actually, here we have 8 bits. Let me to show you. TTL has 8 bits. Okay, and also the protocol has 8 bits. And here, if we receive the traffic from the, for example, TCP, here we will have the value of TCP. The value of TCP is, for example, 6. If we are receiving the traffic from the UDP, the value of protocol is 17. Okay, if we receive the traffic from the ICMP, the value is 1. From IGMP, the value is 2. Okay, from OSPF, the value is 89. From EIGRP, the value is 88. Actually, it indicates the upper layer protocol. Okay, the Internet Assigned Number Authority, or INA, is responsible for assigning IP protocol values. Let me to show you one table for understanding, for learning about different protocols and protocol numbers that we have. And if you want to find the more information, you can go to the ina.org website, and in this website you can find the protocols and protocol numbers that INA assign for different application, different upper layer protocols. Alright, in this table you can see the IP protocol numbers. ICMP, or Internet Control Message Protocol, has the protocol number of 1. Here we can see it. Look at here. About the ICMP, the protocol number is 1, as you can see. IGMP is using the protocol number of 2. TCP, or Transmission Control Protocol, is using the protocol number of 6. UDP, or User Data Program Protocol, is using the protocol number of 17. IPv6 encapsulation is using 41, and then ESP, or Encapsulating Security Payload, is using this protocol number of 50. Authentication Header, or AH, is using the protocol number of 51. ICMP version 6 is using 58. EIGRP, or Enhanced Interior Gateway Routing Protocol, is using 88. Open Shortest Path First, or OSPF, is using 89. And Protocol Independent Multicast, or PIM, is using 103. And finally, Virtual Router Redundancy Protocol, or VRRP, is using 112. Don't forget, this list can be updated, and if you want, you can go to the address that you can see here, www.ina.org/assignment/protocol numbers, to find the more recent version of this table. Alright, now we know about the protocol. After that, here we have again 16 bits for the checksum. Actually, with this checksum, we want to find that this header is noise free or not. Okay, you know that we are calculating checksum in layer 2 and maybe in other layers. This is only calculated on the header of IP, not on the, for example, data. The checksum does not include the data portion of the packet in the calculation. The checksum is verified and recomputed at each point the IP header is processed. It means that, assume that the router 1 sent one packet, okay, to the router 2. Here we have data, And also here we have IP header. Okay, when the packet is receiving to the router 2, first router 2 should compute the checksum for IP header. After comparing the checksum with the checksum of the IP header, it should understand that this packet is noise free or not. After that, it can accept it and it can verify the other information. All right, the next field, as you can see here, is the source address. You know that this is the source IP address, indicate the sender of the traffic. Here we have 32 bits. Okay, and also we have destination address. Again, here we have 32 bits. Let me for example, add the bits that here we have, because I want to show you here. Finally, we have 20 bytes. Look at here, 32 bits is equal to 4 byte. Okay, and again here 32 bits equal to the 4 byte. And after that, let me add these fields together. 8 plus 8 plus 16 again equal to the 32 bits, and also here 16 plus 3, here we have 3 bits, and then plus 13, okay, equal to the again 32 bits, and here we have 4 bits plus 4 plus 8 plus 8 again equal to the 4 bytes. Okay, 32 bits or 4 bytes. And as you can see, 1 2 3 4 5 4 byte equal to the 20 bytes. And after that, we have here the next field. As you can see, the name of this field is the IP option field. In most cases, maybe in 90% of scenarios, you don't use the IP options, but in some rarely cases, we are using the IP options. We are using IP options for some specific features, in most cases for some control functions. Okay, for example, we are using IP options for some security features, for loose source routing, for recording the path or recording the route, and after that for adding the timestamp. Okay, I know that we should talk about them more than this for understand it, but because they are beyond the scope of our course, in this video I'm not going to talk about them. But in each of these features, for example, when you are learning about the loose source routing, you will use IP options. And don't forget, the size or the length of the IP option is variable. If you have multiple IP options, you will have more lengths of the IP options. Okay, and if you have, for example, lower number of IP options, you will have for example, a smaller lengths for IP option field. And finally, as you can see here, we have a field, we call it padding. Actually, the padding is multiple zeros. Okay, this field is variable in length. It ensures that the IP header ends on a 32-bit boundary. What does it mean? Let me give you one example. Assume that here we have IP option field, and IP option field, for example, has 28 bits. This is only one example, and because we want to have at least the boundaries on the 32 bits, here we will add 50. Actually, we are padding this 28 bits or 4 zeros. Actually, we are padding this 28 bits, and now we have 132 bits. Okay, assume that the IP option field has, for example, 56 bits. Okay, and because we want to for example be in the here, assume that this is the, if we have 56 bits, we should have two IP option for example field. Let me use, for example, 10 bits. Okay, for 10 bits we should add 22 0 to the for example IP option, and after that again we will have the boundary at the 32 bits. Because of that, we can understand that the padding size is variable and it is depending to the IP option field's lengths. It is not so important for us. In most cases, it is not necessary to use the IP option fields. All right. Until now, we have learned about the fields that we have in the IP header. Version, indicate the version. IHL, indicate the length of the header. Type of service, it is working for quality of service. Total lengths, it is indicating the total length of the packet. Identification, flags and fragment offset are working for when we have fragmentation. Time to leave or TTL protocol for identification of the upper layer protocol. Header checksum for detecting the noise free or of the packet, or you can calculate the header checksum for understanding this packet is noise free. Source IP and destination IP means source address and destination address, and in some cases IP option field and padding. This is the first topic. in the IPv4 design. But I want to give you a little more information in this video. In this video, let me to use the CCNA video that I have recorded before for understanding more than before about the time to live, or TTL. Actually, in this class, I will use some of the topics that I have used for other courses for better understanding the features that we need for IPv4 design. Let me to use some part of my video related to the CCNA class for better understanding or reviewing the time to live feature. In the next video, okay, I want to explain a little more about the type of service. Actually, again, I will use one of the videos that I have recorded before for better understanding of type of service. Actually, now we are finishing our video, or this video, with the time to live explanation. In the next video, again, we will learn about the IPv4 header and about the type of service specifically. Let me to show you the IP header. This is the IP header. In this course, you have learned about the IP header in some cases, but you will learn more than this about the IP header in this course and also in the future course in the for example, network learning. Look at here, you know that when we are creating one packet, one data with one application, for example, HTTP, we should give this application header or application message to one of the protocols of the transport layer, means TCP or UDP. Okay, after that we should give this segment, this is a segment, to the IP or to the network layer, and in network layer, after adding the IP header, we will have one packet. You learn about this in this course. Okay, after that we will have one packet. And you know that in the network layer, the most and the fundamental protocol is the IP or Internet Protocol. Okay, IP has a header, and in this header, the header of IP, we have some information. One of the most important part of the information in the IP header is the destination address or destination IP. You know that we can use destination IP for routing, for IPv4 routing, and also we have source routing, source IP address. And you know that with source IP address, the destination can find which system sent this packet to the for example, source. Okay, let me to show you one packet in this scenario. For example, assume that we are sending from computer one HTTP packet. Okay, HTTP, and then a TCP. HTTP uses TCP, and then IP header. In this packet, you know that in the IP header we have this information. Source IP is 192.168.110, the IP address of the C1, and destination IP 192.168.210. Okay, because we want to send this traffic from the computer 1 to the computer 10. This is our packet, and we are forwarding this packet to the R1 after adding the Ethernet header and Ethernet trailer. Now I'm not going to talk about the Ethernet. After that, after all of the things that you have learned in this class, the router R1, with comparing the destination IP with its routing table, can find that this packet should forward it over the fast Ethernet 01 and toward the router 2. Because of that, the router 1 is forwarding this packet to the router 2. Again, in router 2, after comparing the destination IP with the routing table of router 2, the router 2 should forward this packet to the for example, computer 2. Now, the computer 2 can accept this packet because the destination IP is pointing to the IP address of the computer 2. But you know that the computer 2 should give the answer or send the answer to the, for example, computer 1. Because of that, as you know, here we will have a packet with destination IP of 192.168.110 and the source IP of 192.168.210. Okay, after that, the for example, TCP or UDP header, this is this TCP because this is a HTTP for example response. And after that, this packet can be sent to the first default gateway, the router 2. After that, with the comparing the destination IP with the routing table of the router 2, this packet should forward it to the router 1, and also after that from router 1 to the computer 1. This is the function of the source IP and destination IP. With destination IP, we can route the packet, we can forward the packet toward to the destination, okay? And with the source IP, we can find this packet received from which system, and we can use that IP address to send back the answer or reply to the sender system. This is a function of the source IP and the destination IP. And you know that in all of the paths, the source IP and the destination IP don't change. They should be same, and they should be fixed, because we need them for forwarding the packet to destination, and after that to receiver, and after that send back one reply. Okay, this is a function of two of the most important field in the IP header. This is the IP header. But in IP header, we have another fields. I'm not going to talk about all of these fields in this video. Only one of the fields, one of the other fields in the IP header are important for us, and we need to talk about that. And that is the time to leave header. time to leave field. I'm going to talk about time to leave, or TTL. Okay, what is the function of the TTL? The TTL is one of the fields in the IP header, okay, and the length of the TTL field is 8 bits, okay. We can say 1 byte, 8 bits or 1 byte. You know that the source address contains 32 bit, means 4 byte, because this is IPv4. And also destination address contain again 32 bits, means 4 bytes, okay? But the TTL has only 8 bit. And I'm going to talk about the function of the TTL, okay? First, we should understand the function of TTL. After that, we can understand the traceroute functionality, and also how traceroute is working and how traceroute can help us for troubleshooting IPv4 routing. Okay, let me to talk about the time to leave. The first thing that you should know is that when a system, for example, computer 1, adding the IP packet, IP header to the data, to the segment, okay, it should set, or it should add one TTL field in the IP header, okay. Here we have the TTL beside of the destination IP and source IP, and TTL is can be set according to the operating system of for example, computer 1. Maybe some operating systems are using the TTL value as 64, another are using the TTL value 128, or maybe some of them 255. Look at here, you know that TTL has 8 bit. Because of that, we can set TTL from 0 to 255, okay. And the number of TTL is not so important. For example, you can use 64, you can use 128, and you can use 255. Assume that here the TTL value is 255. I'm going to talk about the function of the TTL, okay. When each router forwarding this packet, you know that the source IP and destination IP should not change, and this is okay. But the TTL should incremented by 1 value. Time to leave now incrementing by 1 value after forwarding by router, and the new value of the TTL is 254. After that, the packet can receive to the computer 2 again with the TTL of the 253. You will learn about the function of it, okay. And as you can see, in the IP header, the TTL should be decrement from after each forwarding. Here the TTL is 255, okay. Let me to show you. Here the TTL is 255. After that, after sending from router 1 to router 2, the TTL is decreasing to 254, and after that here 253. Okay, now the packet with the TTL of 253 can receive by the computer 2. Also, when the computer 2 give the answer to the computer 1, again it should set the TTL, for example, to 255, and when this packet forwarded with the computer 2, with the router 2, the TTL should be decremented to the 254 and then here to 253. That's it. This is the process of the TTL. But maybe you ask me, what is the function, what is the usage of the TTL? Why we need TTL? Why we need the time to live? What is the function of decreasing the TTL in each router? Let me to talk about that. You know that in this scenario, okay, we have the routing. For example, in R1, we configured IP route 192.168.20.255.255.255.0, then next hop 10.0.0.2. You know it, okay? And after that, this is the configuration of the static route in the router 1. And also, we configured similar command in the router 2, IP route 192.168.10, okay? Then 255.255.255.0, 10.0.0.1, okay? This is the configuration of the static route with the, for example, pointing to the 192.168.10 in the router 2. Because of that, when the packet receiving by the router 2, by the router 1 can use this entry and can forward the packet to the router 2. After that, router 2 can give this packet to the computer 2. Also, from the in the reverse direction, when we are sending the reply from the computer 2 to the router 2, the router 2 can use this entry of routing table and can send the packet to the router 1, and finally router 1 can give this packet to the computer 1. Here we don't have any problem, but in some cases, okay, we are experiencing loops, routing loops. Okay, don't worry about the detail of routing loops now, but let me to say that, assume that we are sending the packet from R1 to R2, and R2 instead of forwarding the packet to the destination can send back the frame to us. Look at here. Don't think about the static routes. Assume that we are sending a packet with the source IP of the computer 1. Look at here, 192.168.110. Destination is 192.168.210, for example, okay? Assume that we are receiving this packet, okay? And we are sending this packet to the router 2, okay? But the router 2, instead of forwarding the packet to the computer 2, now for some problems, maybe the routing problems, again is sending the packet to the router 1 again, and router 1 again now should forward this packet to the router 2, and the router 1 again should send back the frame to the router 1, and so on. This means now we have a routing loop, and forever this packet can be forwarded and again sent back from the R1 to R2 and R2 to R1, okay? And this packet can remain forever in this link. And after that, other packets that are receiving from the computer 1 also are remaining in this link, and after some second you can see the bandwidth of this link, okay, are using, and we don't have any bandwidth, and also other resources such as the CPU resources or other resources in the routers are for example consuming, okay? The reason of this problem is not important now for us, but it is possible. How we can solve the problem? The solution of this problem is the routing. You need correct the routing or the features about the routing. It is not related to this topic, but how we can remove this looped frame, looped packet from this link. The solution is using the TTL. Look at here. You know that when the computer 1 is sending the packet to the R1, it should set the TTL, for example, to 255. Okay. After that, when we are sending from we are forwarding the a packet from the R1 to R2, because this packet now is routed, we should decrease the TTL to 254. Okay, after that, when the router 2 answers to the router 1, again the TTL should be decreased to 253, again 252, okay, again 255, 251, and finally 250, okay, and so on. Because of that, finally, okay, after this, for example, sending the traffic to the from R1 to R2 and sent back from R2 to R1, finally the TTL can reach to 1. Okay, when the TTL is reaching to 1 and the router 1 is receiving a packet with TTL 1, this packet cannot be forwarded again, because after decreasing, TTL will be 0. This means that the for example, the time of this packet is finished. TTL now is 0. Because of that, this packet should be forwarded, and this means that after some sending the packet from R1 to R2 and again sending back from to R2 to R1, after the TTL decreasing to 1, the R1 should discard or drop the frame. Okay, because of that, the function of TTL is not the loop prevention, because the loop related to the routing problems, and you should solve the routing problems. But with TTL, okay, we can remove the packet from the links, okay, and other packets again will for example, experience the same feature. This is the function of TTL in the for example, IP header, and this is the new function for you. Let me to show you first the TTL field in this scenario. In this scenario, we don't have any problem. Because of that, the traffic can be sent by C1 and can be received by C2. Look at here, this is our scenario, PC1 ping 192.168.2.10. As you can see, we are sending the traffic to the PC2. Here you can see the TTL of 62. Let me to talk about this. The default value of the TTL in C1 is 64. Because of that, we are setting the 64. After forwarding, the TTL is 63 from the R1 to R2, and then from the R2 to C2, the TTL should be decremented to 62. Again, from the computer 2, here we have the 64, here we have 63, okay, and finally 62. Because of that, now we are, okay, we can see this 62. This is the ICMP echo reply. The TTL of ICMP echo reply is TTL 62, and we are, for example, experiencing this. Also, if you want, you can capture the links between the router C1 and router 1, and router 1 and router 2, and also the router 2 and computer 2. Let me to show you. This is the capture of this link. I'm going to show you the TTL in this link. Okay, this is the first link. After some second, we can capture also the second link. Look at here. This is our ICMP 192.168.110.2.210. Here, this is the ICMP over IP. This is IP header. Look at here. In IP header, we have these fields. First is the version, then header length, internet header length, then type of service. You will learn about many of them in this course and some of them in other courses. Total length, and then identification, and then flag, and then fragment offset, and then TTL is 64, then protocol, then header checksum, and source IP, destination IP, as you can see. Okay, because of that, the TTL is 64 for the ICMP echo request, and for ICMP echo reply is 62. Look at here, as I mentioned before, 64, 62. Let me to show you the TTL between the router 1 and router 2. First, we should capture this link. This is the capture of the link between router 1 and router 2. Okay, and now again we expect to see the TTL 63 for ICMP echo request and also for ICMP echo reply. Let me to send a traffic again. Look at here. Here we can see the TTL in the ICMP echo request is 63. Okay, and also in the ICMP echo reply, again we have the 63. And finally, in the last link, let me to show you again start capture, again start Wireshark, And now we can send again traffic from the computer 1 to computer 2, and we expect to see the TTL of the 62 in the ICMP echo request and 64 in the ICMP echo reply, as you can see. Because of that, now we know about the function of the TTL. We are using TTL originally for this reason, but with this function we can create another tools such as traceroute.